and hope that it's recording. All right, let's make sure I do this right. Everyone have a syllabus? Let's go over that real quick. So I'm going to assume, I may be wrong, that none of you are new to Weaver. As you may know, I am new to Weaver as of this semester. So I am Dr. Gardner. I got my PhD from the University of Utah. Before that, I got my master's in a really kind of complicated way at UC Berkeley in California. My degree says University of Utah, but I spent no time at the University of Utah. The whole time was up at Berkeley National Lab, which is part of that campus, designing sensors for particle accelerators. I got my undergrad from the University of Utah, but I did a lot of my prereqs here at Weaver, actually. So I started here, ended here. Wonderful little loop. I have worked for L3. I have worked for a neural interfacing company called Ripple, another one called BlackRock. Both of these are local Utah companies, and I work for Lawrence Berkeley National Lab. So I have 7-ish years of industry experience. I don't think I've missed any. I'd actually have to look at my resume. I've been an engineer for a long time now, essentially. So if there are questions you have about industry stuff, like many of your professors, I can answer them. The syllabus is a boring part, and you guys are pretty established at this. So we'll breeze through. I have my office hours written here at the top, but those may change a little bit. I only have hours on Tuesday and Thursday because my Monday and Wednesdays are crammed. I may shift one of those hours to a Friday and do like a Zoom office hour because I can only fit 2 students in my office at a time. So try and email me and schedule ahead of time if you want like a slot in the office hours. You can still show up. I really don't know how busy it's going to be, but this semester is a bit of a special occasion. I think we'll all agree. In this class, I'm going to go ahead and let you do all homework, all lab projects with a partner. So go ahead and pick a partner to work with. You don't have to. If we end up in a situation where there's odd number, you need a group of 3, that's okay. This class can be a lot of work. And you've all taken 2700, right? The digital logic. This is really the next step of that, where we're going to be turning what you learned in 2700, which is really discrete elements, and turning it into system-level design. We're going to be using what we call an Fpga. Anyone familiar? We got one. How much experience do you have with them?
I own one, and I had Slick. We had to actually use them for our labs.
Okay, good. Yeah, so these are very useful tools. They're used widely in industry, especially up here around the defense contractor. And they are programmable logic. So you're going to use a language, VHDL, which I believe you touched on in 2700, to tell this device what the logic gates should look like. And it will assemble itself into a vast system. What we're going to build is pretty simple, straightforward system. You're call it a dumb terminal. You're going to be able to hook up a keyboard to this, type on it, and it's going to display data onto a monitor using a VGA port. The system is fairly simple, but the process of getting there is complicated, and the process is really identical. I designed a very similar system for Ripple Neuro, which is a company I've consulted for and worked for both, actually. And so that's really the goal of this whole course, is to learn how to create digital systems and how to make them talk to each other and timing and all of that stuff. It is a lot of work, usually. So that's why you are allowed to work with a partner. Homework, as usual, make it nice and clear. I will have homework posted usually a week ahead of time, but it will be due a week after it's officially assigned. So there's a schedule online that I haven't printed out because I'm going to kind of continue updating it as we see how the semester goes. But I will let you know as the homework is assigned, it will be due 1 week after that, or 2 class periods. So if we miss a class period, you'll get a bonus on when it's due. Make sure you read this on your own, because I'm not going to go through everything, and I want you to make sure it's known. I'm going to point out some things. One thing I will point out is I'm not sure if we're going to do a final this year because of, I personally think that we're going to make it a month. You can all, maybe we should start a pool, an extra credit pool, whoever gets closest to when we cancel wins. But if we're online, I don't really want to do a final. We may end up doing it. I may substitute it with like a little mini self-contained project instead. So I'm a big fan of project learning. That's what you're here for really, is the hands-on stuff. So that's a possibility. If I do that, the project will just take the same percentage as the final exam. Topic outline. We have a little note here for students with disabilities. You probably, if you have one, hopefully you've already reached out to that office. If you need help and haven't done that, feel free to reach out. There's a link here for the student expectations for the semester, which include wearing a mask, socially distancing, and all that other stuff. Go ahead and read that. Everybody's wearing a mask here. I think in general, engineering students are a little more responsible than the typical student body, and we don't want COVID to send us home sooner than we'd like to. So there are some special accommodations to COVID, and I have this campus closure disclaimer because, let's be honest, it's likely to happen. You've all done lab books before. I'm not doing anything different. I literally stole stuff from Fawn and Night, I guess, before I was here. So I'm not even going to go through that because you guys know how to do it. Any questions on the syllabus or about the course? Great. Okay, cruising along. We can get into it. So today is really just going to be a rather packed review of what you guys hopefully remember from 2700, but for some of you it's been 2 years, 3 years maybe. So that's going to be fun. This is our textbook. I'm really going to be just following along with this one pretty closely to the textbook, actually. This is the same textbooks I used to learn it, with the exception of I actually learned all of what you're going to learn. I learned it in Verilog. So there's VHD and Verilog. We teach VHDL here because defense contractors use VHDL, and that's one of the major hiring bodies around here is government related. So there may be some growing pains with me in the VHDL side because I have many years of Verilog and I have not done much with VHDL until the summer when I've been learning it. But honestly, if you know one, learning the other is not that difficult. Especially if you start with VHDL. You guys are starting the wrong side of it because Verilog is like the Wild West of hardware programming. It's like Python. You can just kind of do whatever you want and it works, but it's not necessarily good. It's a very forgiving language. VHDL is not. Okay, so there are two types of logic, right, that we deal with, and does anyone know the difference between combinational and sequential logic? Okay, so combinational is a lot of what you dealt with before. That is gates, right? What's this? AND gate. OR gate. Yep. You have these ones. Inverter, yeah. And then if you do little things, what does that do? AND gate. You can do the same thing for the NOR gate, right? those are pretty much your major ones. The other one, I'm not sure if you ran into. Yeah, exclusive or XOR. And the symbols that we use for these, right, are sometimes annoying, but they make sense when you get count into, I believe you covered, did you cover Boolean algebra? Yeah. So A and B is multiplication, and or B. What's the symbol for this one? Exactly. And this one? Yeah. Our textbook will actually also use that notation. I usually, if I'm talking about this one, I'll say a tick is what I mean. This is what I mean if I say a tick. You'll find some people say a apostrophe, which is too long, and various others. So if I say a tick, that's what I mean, and a bar is what I'm talking about. Truth tables, you guys remember these? Actually, let me stop for a second. Does anybody not remember this? Caught up? Good. So a simple truth table, right, is going to count in binary, and this is going to be the combinations of A and B, say. Let's do the AND gate, right? Those are not AND. That's not AND, that's not AND, that is AND, right? That's a simple one, right? That's an AND gate. And you can do that for large number of variables. You could have A, B, C, D, E, F, and then some output. And the truth tables come important when you get into digital design because we move into Carnot maps, right? Which we will go over some review in a second of. This book has a nice, which I do recommend picking up. I used this book for years, even after graduating, to be honest. But it has a nice table on page 4 of all of your Boolean algebra laws, right? So you've got some of your basic ones. I'm going to go through and point out some of the more important ones, right? You probably should know all of them at some point, just because they are useful, but let's see, where's a good one to start with? Right, distributive law. Right, if you have X and Y or Z, you can distribute it. X and Y or X and Z, right? Distributive law. One of the more complicated ones that we can get into, do you guys remember De Morgan's law? Can anyone explain to me in just simple terms what De Morgan's law states? No one? All right. So, you can do it?
Yeah, I'm like, I don't know how to explain it.
What's the goal of De Morgan's law?
So if you've got a knot at like the end, you can move it towards the beginning of like both. If you've got everything knotted or inverted, then you can like invert the little pieces and then change the like a plus to times or times to.
Yes, but that's what you're doing. You're substituting knots for.
Yeah.
You're inverting everything. You're ORing and and's ORing, but to do what?
Simplify it, make it smaller, right?
You're actually looking for the complement, right?
Okay. Yeah. Okay. Okay. Yeah. That's
Let me make sure I'm not making that up because it's been a long time. Yeah, it's finding the complement. And that can be very useful. Complement, what does that mean? Anyone?
It's the opposite.
Yeah, it's just the invert. If the output would be 1, right? You're just looking for the inverse of the function. Page 3.
Did you call that a couplet?
Complement.
Oh, complement.
Yeah, there's going to be some. Man, these masks are hot. Vocabulary that may be different from your 2700 class, which we'll start to get into why it matters when we get into the K-maps, because that's really kind of a lot of meat happens in the K-maps, right? You can do a lot of digital design with just a K-map. So I'm going to try and find the good example that they have in here, because I actually like it, because it's overly complicated, but a good example. All right, so they've got this big, bottom page 3, they've got this big equation. Actually, what time is it? I want to make sure I don't run out of time. Doing an example in a book is not going to be the best use if we have too little, but we're good. And you'll notice if you have the book, they're using the ticks instead of the bars, but so this example does a few kind of weird things, like the OR 0, right? What does that do? Nothing, right? Nothing. But they do it just to kind of show the process of what we're doing with De Morgan's laws, because finding the complement can be really very useful in design. And so all you do is you go through for each variable that isn't, and I think they give you a nice like bulleted to-do list somewhere. Oh, it's not bulleted. That's really unfortunate. Is that section 1.2? It's in there. You'll have it in your books. But all you're doing, if you recall from 2700, going through each of the elements and inverting them. And then, if it's an OR, it becomes AND. Now, the tricky part with these is that it has all these parentheses to ensure the order of operation. And you have to make sure the order of operation stands. So if the OR comes first in F, then what we're going to have is F bar. Then the OR is going to become an AND. That AND has to come first. So I'm going to ask, does anybody want me to go through all of this, or do you feel like you could do De Morgan's law?
Refresher.
Raise your hand if you want me to go through it.
Refresher.
Okay, refresher. Okay. So, let me make sure I get my parentheses right, because that's where I always struggle. And that's where you're probably going to struggle, is the parentheses. So this X4 is going to come into this region. And we're going to start looking at E bar becomes E, K becomes K bar, but that's or there, right? And this is also an and, but happening in here. So I'm going to jump in here real quick because that's the innermost that all happens with itself before kind of expanding outwards. A or B. I always hate this one. And D. And now we can erase those. All right? Those two would happen, or with D. Now it's those that happens and D. And then sorry, I'm making sure I don't screw any of these up. I'm going to jump down to this one too because it's inside. Zeros become ones. Ones become zeros. So if we really want to simplify this, and all of this is ANDed with 1, right? What happens to all of this? Yeah, so we can really, in this case, which is nice, they don't do this in an example, but if you see something like this, feel free to be like, and 0. Oh wait, that's or 0. Ha! I almost screwed up. See? That's the and, it becomes an or, which you can then ignore. Sorry, you have a question? No. Okay. Now we got to figure out what we're doing with the C, right? Because the C is in the middle of all this outside-inside stuff. C is going to obviously become C bar, and you've got an OR. What's the order of operations for this C bar OR with all of this? Where do the parentheses go? You can say like...
Would that still stay with...
It doesn't really matter because it's going to be a plus, right?
Yeah. But just for clarity, a lot of times I'll do something like that to break it down. Because what you want to be able to do is when you get to this at the end, kind of back it up and make sure that what you've done makes sense. And once you get to the end, what's a really easy way of checking if you did it right?
Do it together.
Well, you could do that, but that's hard, right? I mean, it takes as much work to invert it. What's the easy way? Yeah. I like this. What I'll a lot of times do is start throwing in specific numbers to make sure that it works. I'll just draw a simple truth table, pick a couple of them out, draw them through on each one, and make sure that it makes sense. Or E or K, or is ANDed. So we're going to have stuff over here. That the bar and this happens first. What I'm trying to get at, right? Because we want to make sure that or happens quickly, and then the and between these two becomes an or. Okay, and or, and now this is where we get a little bit wonky, right? So I got this and becoming an or. The ands usually happen before the or, so now I'm going to need some parentheses to take care of that. And, or, and the parentheses, see. Well,
Parentheses, right? Yes, from before the C and then.
That's, I can just move that one and make it work, I believe. Let me double check this real quick. If I go by the book, the complement of f, x bar, and e or k bar, and parentheses, c bar or parentheses, a bar or d, and d plus 0, and w bar and z, ORed with G or H bar, and 1. I made one mistake. Anyone spot it?
See at the end. Parentheses at the end.
Yeah. Just to make sure that this grouping happens together.
Having closed the first parenthesis. The very first one right after it.
Oh. That one.
Needs to close all the way at the end. After the one. Needs to close.
Yeah. Let's make that into a bracket. I'm not sure I'd give you something quite this complicated on an exam. I might. They're kind of fun once you've done a couple of them. Make sure there's one or two in the homework. But that's the Morgan's Law, and it's all just about finding F bar. You could, in some situations, right, just take F and invert it. There are situations where that will work just fine. Just stick an inverter on the end, but not always true. Most of the rest of those equations on page 4 are there. That's where the simplification comes in for a lot of these. When you're looking like something ORed with 0, it just doesn't matter, or you can distribute and that kind of thing. I do recommend reviewing those. I'll give you again some homework problems, just kind of emphasize what's important there. But what's next is the K-maps. You guys remember these? All right, let's start with a nice, simple one. And a lot of times with K-maps, right, you can either start with a truth table and build a K-map, or you can have a K-map and you can reverse to a truth table. But if I have a truth table, nice, simple 3-variable, actually, can I ask, you guys remember how to do 4, 5, and 6 variables? Or are you guys kind of just remembering the 4?
So it was easy, I remember, but dislike 5 and 6. 5 and 6 is weird.
Yeah, and 5, there's like the easy way and the hard way. But I'll do examples of 4. Well, I might even do 3, 4, 5, and 6. But we'll start with 3 just because it's so easy. It's almost boring, right? And to save some time, we all know how to count to 8, right? I'll figure out where that goes. And 0, 0. Right? Truth table. 3 values means you have 2 to the 3 number of entries. Okay. How do I do my K-map? What's next? I'll make this easy. What do I do? Yeah. Right. What goes here? What do we call this kind of counting? Gray code. Gray code is very useful. It's one of those things that sometimes in your courses you're like, why would I use gray code? It's incredibly useful all the time. A simple example, I was building an analog to digital converter that was measuring some steps through a gray code counter, and I had a very slow amplifier. And there's a problem where if I'm counting up and I go from all the way up to 1, 1, and then I flip back to 0, there's a huge step in voltages, right? Because if I'm building a system that is, have you guys ever done analog to digital converters at all, just at a simple level even? And you have some system, say this is 5 volts max, and your converter is going to have steps. And as it goes up, and it steps up to here, if the counter then starts over, it's a 5 volt drop, which can be an issue. Just by switching to gray code, you can cut the maximum drop that you'll ever experience in half, which is very useful. Okay. What goes here? 0. Do you need me to write this out so it's a little easier? Okay. I'll try that out of the way. Okay, what goes here? We're 50-50 on that one, but yeah, it's a 1. Okay. What's the next step in the K-map? Circles. What are good circles? Yeah, across the top and up and down. What are the optional number values of groupings that you can circle? Powers of 2. So you have 2, 4, 8, 6. Can you do 6? No, 6 is bad. You can do 8, but then it's a pretty worthless map. Then what do? You've got these nice circles, and we know, I'll give you a hint, we know we're trying to get some function. I'm going to switch that over to here so I don't. Sorry, this is the unfortunate thing about this COVID thing, amongst others, is you guys have to be so spread out, and I have to be worried about not getting out of your way. Okay.
Don't you look at that's A naught, B, C naught?
Yeah, so what's the process? What are you looking at?
Oh, you're looking where there's ones, and then what combination makes the 1.
Yeah, so we're looking at each group individually. Each group is going to be a term in this. And when we're doing it with circling ones, each term is going to be separated by an OR. You can circle zeros instead, and each term is then ANDed. is sum of products versus product of sums. Okay, so you have this one. Let's start with this circle. Now, what you're looking for is what variables don't change. So in this first one, what variables don't change? B and C. So those are the ones of interest. What is B in that situation? True. And C? Yeah. The next term.
A is a one.
Boom. There's your function. Right? Nice, smooth, simple, 3-variable K-map. Are we okay if I erase this? This one, I'm going to give you some hinters and then have you run through it on your own. That's probably not the easiest way to do that. You know what? Let's skip the truth table. We'll keep this quick. I won't make you convert the truth table. If I put an X, what does that mean? Yeah, I don't care. Yeah, so I'll just leave the ones, the rest are zeros. Go ahead and start trying to puzzle through that one.
Is it AB on the top and CB on the
Yes, yes. Good question. And I will state this, I have not taught this course before. If I confuse you guys, leave you behind, let me know, because I am pushing through a lot of material right now, just reviewing what was in the last class. If you get lost, confused, speak up so we can make sure that everyone is where they need to be. And if you get finished, just flash your hand up and down so I just know that people are finishing. And if you have a question, raise your hand, leave it up, and I'll. I said I was going to give you a hint. Is there a way to group this one? Yeah. Let me do this with a different color. This is perfectly allowed. When do you stop? When do you know if you have enough circles? All the ones are circled. you're stuck or confused, go ahead and raise a hand. I'll give it about 3 more minutes. Can you put the X in a circle? Is that allowed? Yeah, it's perfectly allowed. You don't care. Okay, so one of the things I'm seeing a lot of people miss, what is the biggest circle that you can do here? Yeah, the top left 4. And any time you can get a nice big chunk of things circled all at once, you want to do that. And I'm seeing a lot of you missing this one. Because those make for a nice big simplification. Do you have a question?
Yeah, you can't circle the ones twice. But...
You actually absolutely can. In fact, we will talk about a design choice later. I think that's this lecture, where there are times when you would want to guarantee that you do that. So once all the ones are circled, you can end up with too many terms, but your choice is when you double this up, right? What you're doing is you're kind of potentially adding extra term, but it's simple. It's a simplified version of that. Sorry, am I right? Okay. So the ones that would circle are the ones that I have now. And then this one has to go somewhere. And really, there's not really any difference between either of those circlings. We all done? Actually, I guess I should ask, is anyone not done? Okay, excellent. All right. Who wants to give me a term, say for the big square? Separated by ors. Who wants to give me another one? Pick one.
The one going from the top to the bottom is a not.
Yeah, I'm just trying to make sure.
That's what I got.
Okay. This guy. Sorry. Say again. That I agree with. Now let's take care of this one way or another. Yep, I like that one. All right. I believe you guys. I just think I screwed up on my notes on this one, which I'm not perfect, and I have not test-driven these. So that's your K-map. You want a nice circle. I highly recommend starting with the big ones because they simplify easier. Remember that you can wrap around. You can even, if you have ones here, you can. That's actually a group of 4. Okay, 5 variables. I probably won't do this one as a deep example. I should not have erased that. So 5 variables, you can do this annoying thing where you make a fat bar, and then you just draw another square here. Oh. Right, and still you're only ever changing 1 at a time, which is what's important. And then if you had a K-map, something like so. Right? Then you just do the same thing with the one ability that you can cross over or like do double loops. Right? And then you have like your standard kind of those ones. All legal. Yeah.
Can you wrap around the sides?
Yes, you can, because if you're going from 0, 0, 0 to 1, 0, 0, only 1, 1 changes. So it is Jason. But that works for 5 variables, so you do something like C, D, E, A, B, right? Something like that, where this is that. This can actually still work when you go on to 6 variable, but it's really not pretty, and it gets a little confusing about what connects to what. So we'll do the 6. Oh shoot! Can I erase this? Okay. The 6th variable, which is quite honestly kind of fun and one of the worst things that you will have to do. So the way the 6th variable works is you're actually going to create 4 K-maps, and they're in a stack. So if you have, I'm not an artist. So you have to picture them stacked like this. And if you had a grouping of 1s in the middle of that, and then under there, in here, you had a grouping of 1s on the lower one, and 1s on that one, and 1s on that one, all the way down through the center of that stack, so that every single one of them, it helps if you draw this right, doesn't it? So all of them have this pattern in it at some level. You can circle through the stack, top to bottom. That makes sense. So here, in this idealized situation, you actually have a group of 16. So you have 4, 8, 12, 16. They could all be grouped together. So, with a real K-map, I'll go ahead and apologize. I am really not an artist. And I will always do my best to make sure that my handwriting at least is legible. It hasn't always been in the past, but I have been improving. On an exam, I will try and provide you with pre-drawn K-maps so you don't have to spend your time drawing them. Again, this will only have to be on the first exam, probably. And all of your K-maps are going to be repeats of some of the variables. But then the other K-maps are all going to be assigned an A and a B. So for this one, for example, we're going to give it 0, 0. That's the top of the stack. This one, what do we think this one is? 1, 1. Exactly. Yep. Because you want this one to be neighbors with that one. Okay. So here's an example, and because we have a finite amount of time, which is good news for everybody, I'm not going to solve all of this, but I am going to have you guys point out some of the more interesting and useful groupings that you can do. So
You got that one down through the stack entirely.
exactly. So you've got this big fat one that is actually a grouping of 16. And that really simplifies things for you because you have 6 variables. But what does this one become?
Is it DF?
It is DF. Yeah, because the D and F are these two guys, right? And I wish I would have, at this point, drawn the F. These guys and D. And those guys. Everyone see that? So that's a nice, easy one. What do you see another interesting group? Something maybe around the size of 8.
One on the left side. 8 cuts to all 4.
Which one?
Yeah, so that one right there you're playing.
Yeah.
Cuts to all 4 of them. Can you do that again?
Yeah, like different color.
Size 8, or just that one.
That one?
Oh, sorry, just the one.
Oh, just this one.
And then going through all.
Well, just
Oh, I see what you're doing. Okay.
yeah.
That one. That one.
That would do 2. Yeah, I'd do 2 wide.
Do I?
And you go through all.
Yeah. You can do that. Absolutely. You can also do a grouping of 8.
Yeah.
See that one? Some of these get really kind of not pleasant, like this 2, right? You can only do 2.
Yeah.
There's no real good way to group any more than that, which is unfortunate.
on the same do wrap up on the same plane.
Okay.
To do the top.
Yeah. Good call.
You can also do 4 if you do it wrap around the other side onto that other car, not wrap. Can't you?
From this one?
No, so that down, that one. Can you move it over to the other one as well?
No. So
Because B is the only variable that changes. Can you wrap on that side?
you could wrap it if this had 2 1s here,
Oh, I see.
because it's over the top of it. You can do really complicated ones, and I never see them. If this had 2 1s, that had 2 1s, this was 1 and 1, you could do that chunk of 8.
I see that.
I never see those ones. That's just
Or if you did like the 4 corners on one and the 4 corners on the next one.
totally loud.
That'd be a weird one.
Yeah, if you guys saw that, if I put that on one, you saw it, it'd probably be extra credit, let's be honest.
You should do it.
Yeah, the exam's like 4 weeks from now, you'll forget by then, it's all right. So I'm gonna stop there. I'm not gonna write out this whole thing, because it would take us the rest of class, probably. Not really, and taking up 15 minutes, but we'll stop there. So hopefully I'll find this. There is another example. I didn't do it because if you want to go review, there's another example in the book on page 7. It walks you through some of the circling options. This book likes to do don't cares a lot. So page 9 has one where they have a 6 variable with a ton of don't cares, just a ton of them. So there's another example that you can use to review. Yes. And there is a list of steps on page 8 I have in my notes. Yep, bottom of page 8. Just in case you guys don't remember and need a refresher, that's where it is in the book. So, there are some terminologies that I skipped that I probably should have started with, but what do we call these groups of ones? Anyone? We call them implicants. Now, there's another, and the reason I'm bringing this up is because there's a term called prime implicant, which is really, essentially means your biggest groups. Prime implicant isn't that important of an idea other than to emphasize we like big groups in this. But that grows onto something that's called an essential prime implicant, which is the largest group that contains a 1 that cannot be contained in any other implicant. So if you're looking at, let's see.
The one in the bottom right corner.
Which one?
The one in the bottom right corner is hard to get.
This guy.
Yeah.
I absolutely agree. So this becomes an essential prime implicant because this guy can't be contained anywhere else. Cool. Moving on from K-maps. I'm sure you're all experts now. This is that brief refresher. Can I erase this? I just realized I am not talking loud enough for that thing. Again, you guys will have an advantage. I forgot to mention this at the beginning. I am going to, well, maybe I did mention it. My brain's all over the place. I am going to record all of these lectures. If this doesn't end up working, I may even make like the condensed version of it for review. Don't try, if you're feeling sick, don't come in. But don't use the recorded lectures as, oh, I can watch them all the night before the exam on 3x speed and do okay. because that's what the undergrad I was teaching at the University of Utah last semester did. And it didn't go very well. Because knowledge needs a little bit of time to steep in, and sometimes you need a little bit of time to realize that you don't understand something. And so when you listen to it, you go, oh, I get that. And then the next day you're going to be like, I have no clue what I was doing here. So feel free to use them as review. And honestly, with digital design, there are tons of resources out there. So if I'm ever talking gibberish and you're afraid of me or something so you don't ask questions in class, there are tons of answers out there online for digital design. Hopefully you guys don't ever get stuck with this stuff. But at the same time, when you're doing your projects, don't go out there and find VHDL code and just copy it and paste it in for your projects, because it will get caught by the plagiarism mechanism, and then you fail the project, which probably means you fail the file. It's not good. So don't copy and paste VHDL code. It is it is a lot easier to catch copied VHDL code than people think. They're like, oh, I'll just change a few lines, it's not different. Like, computers don't think the same way humans do, so the anti-plagiarism stuff is weird. You can work together. You can use the internet for reference. Don't copy and paste the VHDL. Okay. Moving on to designing things. Let's see if I have some decent notes for that one, because I'm pretty sure I wrote them down somewhere. This is, just so we know, section 1.4. Today I'm really doing up to section 1.5 is all I'm going to be doing. Yeah. And then I'll post homework questions to Canvas. I assume everybody here has experience turning questions in on Canvas. Just like a scanned picture, homework, whatever. On Canvas is probably the best way to turn it in during the semester, just to get in the habit of that, because again, I really think we're going online at some point, so we may as well just be ready for that. What I like the face-to-face. I think it's a better learning opportunity. Hopefully we can get enough meat into the class so that when we go online it's not too jarring and we can make lots of progress still. Okay. So this is the design section. Sorry, stopping, gathering my thoughts. This is a lot of material because it's review, and it can be overwhelming for everyone. So if I have a function, I have to use z. So in general, what I try and do, I use f as the function unless f is in the lettering, and then I'll use z. I do the line through the z because my handwriting sucks, and they're not that different. They're 2 and a z, so the line through means z. No line through, it's a 2. Okay. So, equations. Okay, so say I have this function. Is it even worth simplifying? Do you guys see any simplifications that we can do? I'll ask you guys.
Product of sums is good. I said I think the product of sums that it is now is good.
Yes.
The only thing that could simplify out is the d, because that's the only one that's in there twice.
The d?
Yeah, but it's not going to be any better.
I mean, you're kind of right. I mean, better can often be, and this is actually a really good point, better can be subjective, right? Depending how you think about them and what your design kind of considerations are. And sometimes faculty just like to make things complicated. Real function. So what we want to do is create digital logic out of either one of these equations is really fine to create the digital logic out of. And make sure that we know how to build a circuit off of equations, because that can be important. So what you can look at is, again, we just have these groups, and generally you'll start at the output. And the output is the big picture, right? And so if we use this guy to start, now we're going to use this one. There's a reason I like this one. We have an and an and. Our gate at the output then, when you're in this form, right, the product of the sums, your output stage is always going to be an AND gate, right? What is the easiest input to this AND gate? G. G, like it, yeah. What's the other input? E or F, that's a good one. I'm going to make sure I draw this a reasonable way. Right, we agree. And the remaining one is just going to be those ones, which, again, I did this probably just to make your life more complicated. You could do this one and just do that. But this could also cascade into right? We're ORed with B, and we have this mess. So the D comes in. And then you have an AND and an OR. Okay. Bar, sorry. Did I miss any other bars? Just B? Yes. Okay. So this is kind of the cascading logic that comes in here. But there's this idea in digital design that I don't know if you talked about of universal gates. Does anyone know what our universal gates are? NAND and NOR. NAND and NOR can be used to design any digital logic circuit. So something like the Fpga, a lot of it will all just be big blocks of NAND or NOR gates that just get assembled in different ways. These are not universal blocks, right? So NAND and NOR make sure I'm not skipping stuff for you guys. Yeah. Cool. So these are both NOR gates. On page 11 at the top has each NAND and NOR have a different way to be drawn. They have an alternate form. That's it for NOR. This ends at 10:15.
Yes.
So I've got 3 minutes. I'm going to put a pause on this one. We'll get into this next time because I want to address the lab. So this week's lab, again, the calendar is online. This week's lab is just going to be becoming familiar with Vivado, which is the software that we'll use to program it. It is different than what you used last semester. And this is actually new. So we had to replace the FPGAs that we used to have with new ones because we have to give all of you one. We used to do it all in partners, but COVID has changed things. So I had to buy new ones, and the new ones aren't supported by the old software. So there's going to be a little bit of growing pains in that. It's just a slideshow. It'll walk you through first how to install it in Vivado on your own computer if you'd like. I think it has Windows, Linux, and Mac installs. And the second part of it is how to use existing VHDL code and program the FPGA. So all it is taking this light and turning it into a counter. We have lab on Wednesday. You can, if you need to miss, you can just show me a video of you having implemented it, and submit that to Canvas. I will create a lab assignment. I will try to remember. Or you can come and I can help you walk through. Having Vivado on your own laptop is useful. So that's why I have it installed. But it is like 30 gigabytes. If you don't follow the examples and you just were to install it, it's like 50. So I've kind of pared it down to just what you need. Anyways, that's the lab. I have 1 minute. Let me make sure you guys aren't any other confused. Do you have any questions?
As far as the lab goes, it looks like the PDF is not full.
Oh, I have to update that. Sorry. There's some weird crossover. There is a viable file in the files.
It's just not the efficient.
Okay, I'll try and fix that today. Any other questions? Yeah.
So with the boards, we like each pretty much check one out for this.
We will check one out to each of you. Yes.
Is that going to be just Wednesday when that happens?
Yes, that will be on Wednesday. The third edition book probably works as well because there is a third edition. We want the older because there are more used copies. If you get a third, the only difference might be the questions. And if you end up with the third, if somebody ends up with the third edition, let me know, and we'll make sure that you get the right homework questions. I think that's the only thing that's really going to be a difference. Digital logic hasn't changed in 30 years, so.
I was confused, like,
Yeah, no, we put.
why did that happen?
What? Yeah.
I wanted to book that from ESU, and then had to transfer back.
Oh, did you?
So, yeah, last year was kind of the...
Sorry, was that the Arizona State Online?
Yeah.
How was it? I'm curious.
It was actually fantastic, but you have to pay out-of-state tuition when you're online. And I think the big problem with student loans like that is just enough information until it's too late. So it's like, yeah, paying out-of-state tuition, and then getting to like the aggregate limit for federal loans, like forced me back to Weaver State because it's like $2,500 a semester. There, it's like $9,000.
Holy crap!
It's actually not too bad for out of state.
It's not too bad, but it's just bad enough.
I'm curious. I have a couple of siblings that are in engineering,
Yeah.
and they're debating.
I love.
I will try not to be terrible for you. I'm new. So work with me on this.
So far, it's been good because I remember I took digital systems before I transferred to ASU. I didn't finish the class. I got like 3/4 of my class. There's a lot of stuff in the review that has been covered that I saw covered at ASU that I never saw covered at Weaver. And when I came back here, so it's been about a year, and all the professors are different, and everything's kind of changed. So I'm kind of looking forward to the change in how it's being taught that comes along with that, because with the defense contractors being a big hiring force, I feel like Weaver State has always been much more geared to that than any of the other universities around here.
Yeah.
So.
Yeah, no, I went in, one of my freaking interviews that I did, because I interviewed after my bachelor's, I interviewed after my master's, and I just kept going and turning down jobs. One of the exams I actually got was literally for on semiconductor. They handed me, it was a quiz, of this stuff. They're like, here's a K-map, solve it, here's it. And I was like, I don't know what to do.
Like I didn't understand before why we would even do more than things until I went to ASU and they said, oh, because you have like pull down and pull up networks, then it's easy to find the complements to do like the transistor level design and stuff like that.
Yeah.
Okay.
Yeah, I try and like make it applicable, but I didn't get through all of what I was supposed to get through.
Yeah.
The review is just so dense, and it's hard when I have new students. I don't know what you guys know, because I didn't do EE at Weaver,
Yeah.
and I haven't taught any of you, so I'm in catch-up mode.
Yeah, it's all different because I did mine like a year ago anyway, so it's all changed since then.
Okay. Well, thanks for talking. I've been curious about ASU. Yeah.
All I was going to say is everything that you do is review basically how, like I had Dr. Brown for it, except for the multiple variable K-maps, he just always did variable, or what do you call them? Okay, but it'd just be like, the one 4x4 K-map, and then you'd put like instead of E, you just put E, like a variable entered K-map. I think that was
the map entered variables.
Yeah. That's how I think everybody in the class learned it.
Okay, interesting.
So I looked around, I could see that when you're doing the 4 K-maps at once, I don't think any of us have seen that before.
Good to know.
I think Brown and everybody else did the variable entered maps.
Okay, yeah. I've never done the variable entered maps. I always do it the stacked. But the result is really the same.
Yeah.
And it won't be a huge part of this class.
Yeah.
To be honest,
just letting you know.
it's just to make sure. I appreciate it because I don't know these students.
Also, you know where module 2 is?
I think that's the portables that are just upstairs and outside.
Okay.
I believe, but I could be wrong. You guys are 2700.
Correct.